Hello everyone, welcome to Module 3, Datum and Datum Selection. What is datum? Datum is a theoretically exact point, axis, line, plane, or combination which can be derived from theoretical datum feature simulator. So we can see here, there's two terms, datum and a datum feature simulator. We're going to explain that later. Datum system is a set of symbols and rules that communicates to the joint user how dimensional measurements are to be made. We are going to use data system to measure parts based on the datum we specified. Here's one example. How could we specify the datum to the parts? First, why do we need datum? Let's have a look at this picture. We want to know the height of these two basketball players. Here we go. Now we know the height of these two basketball players if we know the datum. Here we know the ground is a kind of datum. Let's look at the real parts. Here is the CAD model of theoretical part. And here is the actual part. Obviously, these two holes is off the center. And we want to know, is this position of the hole too low or too high? From here, we don't know. If we use this as a datum, then that means here is too low, right? And if you rotate these parts, you use this as a datum, otherwise this surface is here. Then the position of these two holes are too high. So from here, we know datum is so important for us to measure the parts properly. But how could we find the datum from real part? Here is the theoretical part, or sometimes we call this mass data or CAD model. Here is the real part or actual part. Please remember, all of the real part or actual part always has deviation. It's not perfect. This surface is the bottom surface. It's not perfect plane. Where is the datum? How could we find the datum from this real bottom surface? Before we understand where's datum, we should understand some important terms about datum. First, the real bottom surface, or the physical portion of the bottom surface from actual part, we call this bottom surface is datum feature. Please remember, it's a feature. Datum feature. It's not perfect. The datum what we want is the highest contact surface of this datum feature. We call this true geometric counterpart. And it's supposed to be perfect. But in real world, there's no such a thing as perfect. Practically, we are going to use some simulated datum to simulate the perfect datum. For example, machine tables or marble tables of CMM or surface plate. We can use those kind of planes or simulated surface as a datum is not perfect, but they all have such a quality that is good enough for us to measure the geometric tolerance. This simulated surface, we call this datum feature simulator. And sometimes we call this simulated datum or datum simulator just. Please remember, datum feature is not datum simulator. Feature is the physical portion of the parts. It's not perfect. Datum simulator is almost perfect. We use datum simulator to simulate the true geometric counterpart. As we mentioned, datum simulator such as machine tables are not perfect, but their quality are good enough. Or we can say the error of their deformation is small enough. It's good enough for us to use it as a true geometric counterpart or use this datum simulator as a datum. As we mentioned, datum simulator is the tangent plane. What is tangent plane? It's the highest contact surface from datum feature. So we call this tangent plane. But actually, there's all kinds of different datum feature simulator or datum simulator. We just know there's a tangent plane to be used as a datum simulator. There's other kinds of datum simulator, such as maximum material boundary or MMB, least material boundary or LMB, actual mating envelope ME, or there's some other kinds of datum simulator. We are going to learn all of these different types of datum simulator in the later module. Let's have a short summarize. Datum simulator from a plane shall have the following requirements or characteristics. First, it's supposed to be perfect form. Even the datum feature is not perfect, but the datum simulator is supposed to be perfect. Second, all of the datum simulator supposed to have a basic orientation related to one another for all of the datum reference in feature control frame. It's a little bit hard to understand because there are several terms here we are not taught yet. But again, as we said, datum should be datum simulator or datum should be perfect. It talking about form should be perfect. Orientation should be perfect for any datum related to the preceding datum. Another one is location should be perfect. This is why we say basic location related to other datum feature simulator or to preceding datum feature simulator. Unless there's a translation modifier or movable datum target symbol is specified. We are going to learn what is movable datum simulator and also datum target. When the datum has MMB or LMB, usually the datum simulator size is fixed. If the datum feature applies at RMB, the size is adjustable. So what is MMB and what is LMB and RMB? This is all related to the datum chapter we are going to learn in the later module. But so far, we should remember, if datum feature is a plane, the datum simulator is supposed to be perfectly formed to reflect datum what we want. This is the key concept so far we should understand. Datum is perfect form. We are going to use datum simulator as a datum. Datum feature is not datum. There's another question. As we mentioned, datum simulator should be always the highest tangent plane. But what about the bottom surface of the actual parts is convex? That means this is not stable. But how could we find the tangent plane? This part is going to rotate. The proper way to find tangent plane is to balance these parts according to the theory of minimax. That means we are going to use the way minimax here, minimize the maximum deviation. There's always some place there's a deviation from datum feature to the tangent plane. We try to minimize the worst deviation. This is why we call this minimize maximum deviation here. Sometimes we call this Chebyshev association. Chebyshev means to minimize the maximum deviation from the datum feature to the tangent plane. From this method, you can find a unique datum. When we specify the datum, we should never use the implied datum. So what is implied datum? Look at it showing here. There's a center line here, and there's a datum A here. We call this implied here. This datum, we cannot find it from anywhere. Because when we try to measure the parts, we don't know how to get this center line from real parts. Let's have a look at the real parts. The real part is not perfect. This cylinder, we are going to deviate it from this cylinder and this cylinder. Same, the center hole, we are not be coaxial with all of these cylinders. We are going to be off the center. From here, we don't know which axis is talking about. This axis can be get from different cylinders. We can get this axis from the hole. We could also get this axis from this cylinder or the common axis of this cylinder and this cylinder. There's many ways to get this center line as a datum A. And all of this datum axis is not going to be overlap. It's not going to be the same axis. This is why we said datum should never be implied. We should always tell the joint user clearly from which feature we could get this center line. This is why we're going to use the datum specification, how to specify the datum properly to let other people understand where this datum A come from. When we use the datum system, it's going to provide 3 key benefits. First, it will help to make repeatable dimensional measurement. The measurement is repeatable. The second, it helps communicating the function of the part to the user. Third, you're going to make dimensional measurement as intended by designer. Once designer make the specifications of geometric tolerance, there are some function intention with the proper datum system. The inspector is going to measure parts based on the expectation or intention of the designer. When we look at join, datum is all about one of the key concepts for us to understand the geometric tolerance. Here is the typical composition of geometric tolerance. For this rectangle frame, we call this feature control frame. That means we're going to use this rectangle frame to control the feature or to control the geometric tolerance of the feature. This red line, we call this tolerance zone. We're going to explain what is tolerance zone later. And this one, the top physical surface, we call this tolerance feature. This geometric tolerance or profile has a datum A, and datum A is the bottom surface. Where's datum A? We have just learned datum A is the tangent plane from the actual bottom surface. It's supposed to be a perfect tangent plane. As we mentioned, it's very important to specify the datum to the join properly. But how could we select which feature supposed to be used as a datum? There are some rules. When we select datum feature, the designer should consider the following characteristics. First, we should consider function surface as a datum. Next one, mating surface. The other one is the surface supposed to be readily accessible. If the surface cannot be accessible by the inspector, then it's going to be very difficult for them to measure the datum. The datum surface is supposed to have sufficient size to allow repeatable measurements. So this is why we're going to bring in details how could we select the datum. You're going to reflect function and assembly requirements, and it's supposed to have sufficient size to orientate or stabilize or locate parts. Let's have a look at one example, how to select datum. There's a part A here, there's a part B. There's two parts. Part B and part A are going to assemble it together. The question is, which feature is supposed to be selected as a datum? Are we going to use this pin as a datum? Or are we going to use this bottom surface as a datum? The answer is, we don't know. Why? Because we don't know the mating relationship between part A and part B. Let's have a look at the first scenario. The mating relationship of these two parts is we are going to use this pin and this hole as a mating or interfacing. The pin is going to assemble it into the hole, or we're going to use this pin to locate parts. The bottom surface is going to have some distance to another one. In this situation, the datum supposed to be specified to the pin, not to the bottom surface, because the pin is the mating surface, or it's the mating feature. In other situation, if the part B touch the bottom surface first. And then we're going to push these parts into the datum A. In this situation, the bottom surface is the mating surface, or the mating feature, because you're going to touch the bottom surface first. You're going to locate parts with this bottom surface. That's why we're going to change the join to specify the datum to the bottom surface here. And this pin is not datum anymore. It's going to be tolerance feature, or the feature to be measured, or the feature to be toleranced. So we can have a quick review here. If the locating relationship is through the pin and hole, the datum supposed to be the pin. If the locating relationship is between the bottom surface and the bottom surface, then the bottom surface supposed to be used as a datum. Which feature supposed to be used as a datum is decided by the function of the parts. This is exactly what we mentioned here. On the basis of the function and assembly, we could select which feature to be as a datum. Datum features are selected on the basis of a part function and assembly. Let's have a practical practice here. There's a part A, green part B, brown part. We are going to assemble these two parts together. From the assembly requirements, we know this is the mating surface. And these two pins and these two holes are the next mating surface. Now, based on the function, we are going to specify the datum. Datum A is the mating surface, the bottom surface, for the green parts. Datum B should be specified to the two pins, because these two pins are the locating features. If you look at these assembly requirements, here is the mating surface, here is the locating features. Now we get datum. Again, let's have a short summarization. Based on the function, we select the datum, or datum selection is based on the function of the parts. From here, we have a magic 3 steps to make a proper join. We call this design for function magic 3 steps. Step number 1, we should understand the function first. Step number 2, we specify the datum based on the function or assembly requirements. Step number 3, we specify the tolerance to the parts. This tolerance means 4 types of tolerance. As we mentioned before: size, form, orientation, and location. Let's repeat it again. Magic 3 steps to make a proper join. Step number 1, understand function first. Step number 2, specify datum feature based on the function or assembly requirements. Step number 3, specify the tolerance, which including size, form, orientation, and location. Mostly you're going to use all of these symbols to express the geometric tolerance. And here is plus minus size tolerance. As we mentioned before, the datum feature to be selected supposed to have a sufficient size or length. Here is one example to explain why. If you look at this part, you may notice the length of this pin is a little bit short. The datum A is specified to the pin. Why this is not good enough for us to use this short pin as a datum A, we are going to explain soon. Because the length of the pin is short, that means if there's a little minor tilt or rotate of this pin, the datum simulator or the datum axis we get from this pin is going to sway or tilt geometrically. Just imagine if this pin rotate a little bit, the axis is going to rotate accordingly. Eventually, we're going to use this axis as a datum. And you could understand it's going to have a big exaggerated arrow, because from the short pin, it's not easy to get a stable datum axis. And the datum should be always extended, right? It should be always extended. From a functional point of view, it's not good practice to use the short pin as a mating feature or locating feature. If the length of this pin is too short, then the function of locating two parts is not going to be stable. It's not good practice to use short pin, right? You may ask how long it's going to be good datum. The answer is all based on the function. If the function is okay, then you can use this. From a measurement point of view, you can always use the measurement system analysis to verify that the measurement is repeatable or not. All right, let's have a quick review about Module 3. In this module, we explained very important key terminology. What is datum? What is datum feature? And the datum feature simulator. And we also explained the principle. How could we select the datum feature? Should be based on the function of the parts or based on the assembly relationship. Thanks for watching. We will see you in the next module.